Hi there. In this second part of the lesson, we'll continue discussion about the deformation of axially loaded members. In the first part, we'll learn about how these deformations are calculated. They're generally useful to calculate for design purposes, so to check that the deformation of a member is not beyond the acceptable limit. But also, we'll see here that they are very useful and handy when trying to solve statically indeterminate axial load members. So we have here this member that's fixed at A and C and loaded somewhere along its length at point B with force P. If we try to solve for the reactions of this member, I will have to draw the free body diagram. Of course, fixation at A and C will have 3 reactions in 2D problems, but because I see here there is no transverse load, so I will ignore the moment reaction and also the horizontal reaction at the fixed supports at A and C. So I have only one reaction for A and one reaction for C. If I apply the statics here and equilibrium, you will see here sum of forces at Y direction. I have FA plus FC, negative P is equal to 0. And because I kind of excluded any moment action or horizontal force equilibrium, I'm only left here with one equation and 2 unknowns, assuming that P is given. So I need a second equation to be able to solve for FA and FC. And we'll see now deformations will come to save us here, literally save us, because we are stuck, we are needed in one equation. So using the deformation information, we'll have kind of 2 similar methods to apply this information to solve for this one additional unknown. So the first method is the redundant force method, and the second one is kinematics. For the first one, redundant force method, I have to kind of go over a view of one method that we covered in statics, which is superposition. So superposition, I will illustrate with this beam here example. And the idea here, this beam is loaded with different load cases, and so I a point load F, distributed load W, and a point moment load M at the end of it. So to analyze this beam and kind of figure out anything I want about it, I can actually apply the divide and conquer strategy. So the idea is I will copy this beam and apply for each copy the different loads I have independently. So I have the point load in the first, the distributed load in the second, and the moment load at the third. And the promise here from the superposition is whatever I add up the values of a variable from the 3 cases of the beams, the same beam, it will add up to the original value that I should have supposed to get if I solve the original beam with all the loads on. So if I solve every beam separately now with these individual loads, I can add reactions out of it, I can add the stresses from each one, I can add also deformations from each one. So as an example, I have here these reactions RA and RB in the original beam. RA, I can say it's equal to the reaction RA1 from the first beam, RA2 and RA3 from the other 2 beams. And RB1, RB2, and RB3 will add up to the original reaction RB in the original beam. So it's pretty handy. Like I can, in some load cases, I can use information that are in textbooks. So for a point load on a beam, a lot of textbooks give you reactions for it, or you can actually memorize it. You can calculate the deformation at one point from tables and textbooks. And you don't have to solve and do a lot of calculations to figure out for the original beam that has multiple loads in it. I can add the impact of each force on the beam, add this impact to end up with the original case that I had. So this impact can be finding reaction at one support, or finding the stress of at one point. But here, one thing, kind of a disclaimer we have, is you can only do that if all these forces will result in the beam behaving in only the elastic region. So if I did all of that and at the end calculated the stress and found it's beyond the proportional limit, then this whole effort is wasted and I actually have to use a completely different type of analysis. So here, this is just a very careful, this is something we have to be very careful about, is the behavior of this beam should be always within the proportional limit, because in proportional region or elastic region, the behavior is linear. So I can add the values and the assumption here in linear behavior. This addition will bring you to the original load case and its impact on the beam. So that's just an intro to how to solve statically indeterminate axial loaded members. We didn't solve this axial loaded member yet. We just introduced there are two methods, the redundant force method and the kinematics method, and kind of the superposition is the way to deal with the redundant force method. So in the next two videos, we'll cover each one of these methods. So stay tuned. I'll see you in the next part.